Hello and welcome to the beginning of Chapter 7. We're going to take a look at some introduction to algebra. Algebra basically does the same things that we've been doing with numbers, but then applies them to variables. A variable is just a symbol, a letter usually, so A or B, X, Y, anything along those lines. It represents a number. So Y could be 4, or I could change it, right, and make it into an 8, right? Whatever I choose Y to be, that is what Y is. Now once we take a look at equations, equations will tell us what that variable is supposed to be, but until then, when we are looking at expressions, which we'll take a look at in just a sec, we will be able to choose what value the variable is. So just a couple things before we get to expressions. Let's take a look at multiplication with variables. Okay, if I have A times B, right, I can represent that multiplication with a dot or with parentheses. A times B, or A in parentheses, times B, or A in parentheses and B in parentheses. All three of these mean A times B. The most common way to see it though is A and B written right next to each other with no symbol in between. This also means multiplication. So get used to looking at that. Right? Anytime you have a variable next to something else, or even a number next to a variable, and this implies multiplication, A times B or 2 times B. Right, when they're just written next to each other. An expression is just an operation or operations of variable terms. So for example, 2x plus b minus 4, this is an expression. The only difference between an expression and an equation has an equal sign, right, and then something else on the other side of the equal sign. So this is now an equation because it has that equal sign. A common form of an equation is the formula. It's just an equation that has a common use. For example, right, V equals IR. Right, this is Ohm's law. Right, the voltage is equal to the current times the resistance. You can also have D equals RT. Right, this is distance equals rate times time. Just another common formula. So let's take a look at evaluating some formulas. If I have this formula, J equals 3/4 L plus 1, if I want to evaluate that formula, I need to know what L is equal to. The problem will tell me L is equal to, say, 44, and then to evaluate a formula, I just plug in the value of L to where L is in the equation. So J equals 3/4 times 44 plus 1. And then I follow my order of operations. I do what's in parentheses first. Then I take a look at roots and powers. And then I take a look at multiplication. So this is the next step in this equation. 3/4 times 44, that's 33. So I have 33 plus 1, or J equals 34. So that is evaluating an equation or formula. We can make it a little more interesting with this formula. R equals D squared N all over 2.5. For evaluating an equation, we need to be given the values of the variables within that equation. So we need to know what D equals and what N equals in order to evaluate this equation. D in this case is 3 1/2, and N is 6. So if we evaluate this equation, R equals 3 1/2 squared times 6 all over 2.5. Right, we carry out our root first, 3 1/2 squared, which is 12 1/4 or 12.25, and that's still being multiplied by 6 all over 2.5. Next, we can multiply together our 12.25 and our 6, which gives us 73.5 all over still that 2.5. Finally, if we want to find out what r is equal to, we will divide 73.5 divided by 2.5, which gives us 29.4. Then we've now evaluated this formula and found that r is equal to 29.4. Back in chapter 5, we took a look at how to convert between Celsius and Fahrenheit using a table. Now we can do so with an equation. If I have F equals 9C over 5 plus 32, this formula will allow me to plug in a value for C degrees in Celsius and then evaluate the formula to find out the equivalent degrees in Fahrenheit. So if I want to find what degrees Fahrenheit it is when our Celsius is negative 160, we can plug that in for C and solve for F. So F is equal to 9 times negative 160 all over 5 plus 32. Now, according to our order of operations, we multiply 9 times our negative 160 first. So Fahrenheit is equal to 9 times negative 160, which is negative 1,440 over 5 plus 32. Negative 1,440 divided by 5, we do that division before adding, and we get negative 288 plus that 32. So our Fahrenheit then is negative 288 plus 32, or negative 256 degrees Fahrenheit. Now let's take a closer look at some algebraic terms and what we can do with them. First, what is a term? A term is a part with a number and a variable. So this is a term. Another example of a term is 3x squared. Again, this is a term. If I add these two together, this whole thing is not a term, but it is the addition of two terms. So again, a term is just the one piece that has things multiplied together, right, with a number part, so what is also called a coefficient, and a variable part. And it can have more than one variable and still be one term. So this is just one term with a coefficient or number part of 3 and variables y and x. The reason we need to be able to identify terms is so that we can identify like terms. Like terms have the same variable part. So here 3x and 2x, these are considered like terms because they both have the variable x and it's raised to the first power in both cases. We do not write the first power just because it is redundant to say x to the first power. So we can add these two together, and in order to add like terms, we just add their number parts, their coefficients. This is basically saying I have 3 apples plus 2 apples, and that gives me 5 apples, or 5 x's in this case. Okay, whatever makes it a like term, that x variable has to stay the same when you add them together. The only thing that changes is your coefficient, your number. Okay, some more examples of like terms would be 2x squared and 5x squared. Again, they have the same variable raised to the same power, or even 3yx or 2xy. These again are like terms. They have the same variables, and each variable is raised to the same power. It does not matter that they are being multiplied in a different order. They are still like terms, and I can add them together. So for this first one here, right, again, 2 plus 5 is all that I'm changing, and then what made it a like term stays there the same. So 2x squared plus 5x squared is 7x squared. 3yx plus 2xy, right, that 3 plus 2 gives me 5, and then I can choose which order to write the variables in this case, usually in alphabetical order, x, y. So 3yx plus 2xy, 5xy. This is different than, say, 3x plus 2x squared. Something like this, you cannot add together. 3x plus 2x squared, they are not like terms, so if you wanted to try and simplify it, you just have to leave it as 3x plus 2x squared. You cannot change anything to it unless you know what x is supposed to be. And then you could evaluate it, but you cannot simplify or combine terms here because they are not like. Let's also take a closer look at some expressions. Let's say I have 3x plus 2y minus x plus 7y. This again is an expression because it does not have an equal sign. I can simplify this expression though by combining like terms. So here I need to identify the like terms. I have an x term here and an x term here. Then I have a y term here and a y term here. Those are my like terms. Thanks to the commutative property, I can add things in any order. So this 3x minus x, I can do that all in one step, even though there's a 2y in between it. 3x minus x, this is the same as minus 1x. So 3 apples minus an apple, right, gives me 2 apples or 2x. Then 2y plus 7y again, I have a positive 9y. And now this is my simplified form. Right? I cannot simplify any further because they have different variables here. So this is my simplified answer. Let's say I have 2 open parentheses x plus 3. Something like this is again an expression, and I can simplify it using what is called the distributive property. Right? What I do is I distribute this 2 to each item inside. Again, as we mentioned at the beginning, anything written next to each other, so this 2 times this x plus 3 in parentheses implies multiplication. So what I'm doing is I'm multiplying this 2 by the x and multiplying 2 by the 3. 2 times x is just written 2x, right? And then I'm adding that to 2 times 3, which is 6. So I've now simplified this expression. Another example of this, negative 3 minus x. Okay, again, now it's just a negative sign outside. We can treat this as a negative 1 being distributed to what's inside the parentheses. Negative 1 times 3 is a negative 3, and negative 1 times a negative x is a positive x. So anytime a negative times a negative, it makes it positive. So this is my simplified form. To put this in a little larger context, we can take p minus 2 times negative y minus 2x. Right? If we want to simplify this, what we have here is multiplication. According to our order of operations, we always do this first. So we're going to take this negative 2 here and distribute it to what's inside the parentheses. So I have p minus, so negative 2 times a negative y, that actually makes it a positive 2y, and negative 2 times a negative 2x makes it a positive 4x. I then look at this to see if I have any like terms, which I do not, so this then is my final answer. Let's now take a look at some equations. Say for example x plus 3 equals 7. Now it's kind of clear to see that this x should be 4 in order to make this equation true. What we can do is say x equals 4, right, and then plug in that 4 into this equation to go ahead and verify that x equals 4 is the solution to this equation. So we plug in our 4 plus 3 equals 7, and indeed 4 plus 3 is 7, which is equal to our 7. So when we get this here, 7 equals 7, or something true like that, it shows that this answer that we checked is indeed the correct solution. If we take a look at x squared plus 6 equals 5x, in this case it may not be clear to see what our solution is. Let's go ahead and check to see if x equals 2 is a solution. Here again we just plug in 2 in for x, and we have 2 squared plus 6 is equal to 5 times 2. So 2 squared is 4 plus 6, 5 times 2 is 10, 4 plus 6 is 10, which is equal to 10. And again we have something true, which means x equals 2 is a solution to this equation. Now we won't always be given the solution to an equation, but we can use certain properties to find those solutions. Take for example, if I have 10 equals 10, if I were to subtract both sides from this equation by 2, so 10 minus 2, that gives me 8. As long as I did the same thing to the other side of the equation, I will also get 8, and I will still get something true. We can use this idea in order to solve equations. For example, our x plus 3 equals 7. We can solve this equation to show that x equals 4 by using this idea. Here we have x plus 3, but we want to just show x equals 4. So we need to get rid of this 3 here on that side of the equal sign. If we were to subtract the 3 from both sides of the equation, right, we would have just our x here. 3 minus 3 is 0, so I don't need to put anything there. And that is equal to 7 minus 3, 4. And I get that statement, x equals 4, which is what I wanted. We see here that as long as we add or subtract something to both sides of the equation, we will still get something true. And in that case, it will help us to solve for that unknown variable. So to solve x minus 7 equals 10, I could then add 7 to both sides so that I just have x left on this side of the equation. Since negative 7 plus 7 is 0, that gives me 17. X equals 17. I can then show that that is the solution to this equation by plugging 17 in for x here. So 17 minus 7 equals 10. And indeed 17 minus 7 is 10, showing me that 10 equals 10, a correct solution. Another interesting idea is multiplication. Say I take that 10 equals 10 again. If I divide both sides of this equation by 2, that will give me 5 over here and 5 over here, again giving me something true. Or even if I took 10 equals 10 and multiplied both sides by, say, 3, right? 3 times 10 is 30, and 10 times 3 is 30. Again, I have something true. So if I divide both sides of an equation by the same thing, or multiply both sides of the equation by the same thing, I get something true. I have to be careful with this, however. If I have 2 plus 3 equals 5, this indeed shows, right, 2 plus 3 is 5, that is true. If I multiply both sides of this equation by 2, right, I need to make sure that I'm multiplying everything on this left side of the equation by that 2. If I don't, this is what happens. Here I get 2 times 2, which is 4. And then I have my 3, 5 times 2 is 10, and it tells me that 4 plus 3, which is 7, is equal to 10. Well, that is not true. The correct thing to do is to treat this whole left side as one piece. Now I am multiplying 2 times 2 and 2 times 3. 2 times 2 gives me 4, and 2 times 3 gives me 6. That is equal to now 5 times 2, 10, and indeed 4 plus 6 is equal to 10. So the real key here with multiplying and dividing is to make sure that I multiply everything on both sides by that same number. Let's take, for example, 27 is equal to negative 3x, and I want to solve for x. In order to get x by itself, I need to do the opposite operation to this negative 3. Here I have negative 3 times x. So to get rid of that negative 3, I'm going to divide by negative 3. If I do it to the one side, I have to do it to the other. Here, negative 3x divided by negative 3, my negatives cancel out and my 3's cancel out, and I'm just left with x on this side of the equation. Now 27 divided by negative 3 gives me a negative 9, and I see that negative 9 is equal to x. I can then verify this by plugging negative 9 into the original equation. So 27 equal to negative 3 times negative 9. Negative 3 times negative 9 indeed is 27, and I have 27 equal to 27, which is true. So x equals negative 9 is my solution. What about negative x over 4 is equal to 3? Well, in this case, again, I want to get x by itself, so I need to get rid of this 4. Currently, I am dividing by 4, right? A negative 4. So if I multiply both sides by a negative 4, I will be able to get rid of that 4 here in the denominator. Negative 4 times a negative x over 4. Right? The 4's then cancel out. My negatives cancel out, and I'm just left with x on that side of the equation. 3 times a negative 4 gives me a negative 12, and that is the answer to my equation. Now let's go ahead and combine all of these ideas. Let's take 3x minus 7 equals 11. My main goal is to get this x by itself, right? So at the moment I have 3 times x, and 3x, right? That term is being subtracted by 7. The first thing I want to do is get just x terms alone on that side of the equation. So first I'm always going to add this 7 to both sides of the equation. This leaves me with 3x equal to 18. Now I just have the x term, and to get rid of the 3, I can divide both sides by 3, just leaving me with x equals 6. So 6 is my final answer. I can check that solution. 3 times 6 minus 7 equals 11. 3 times 6 is 18, minus that 7 equals 11. And 18 minus 7 indeed is 11. So we have a true solution. Let's do 5x over 3 plus 5 equals 30. Again, I'm going to get the x term by itself first. So I'm going to subtract the 5, minus 5 from both sides. Okay, I always do the opposite operation. If I'm adding 5, I subtract 5 from both sides. If I had that negative 7, then I add 7 to both sides. This leaves me with 5x over 3 is equal to 25. Now 5x over 3, right, this is basically 5/3 times x, right, is equal to that 25. To get rid of that fraction, I can multiply by its reciprocal, 3 over 5. If I multiply by the reciprocal, it cancels out that fraction. Now if I'm multiplying by 3/5 on this side, I have to multiply by 3/5 on the other side of the equation. Here, 5 and 5 cancel out, 3 and 3 cancel out, leaving me just with x, and 25 times 3/5. Right? If I want, I can change this into a fraction to make the multiplication a little easier. There's a common factor of 5 here, and I have 15 is equal to x. So if I were to plug 15 back in for x into the original equation, it would indeed give me a true solution. I will leave it to you to go ahead and test that. That will do it for the first 4 sections of Chapter 7. Be sure to take notes on this and bring in your homework for the first 4 sections of Chapter 7 to class. Also, don't forget to bring whatever questions you have for me, and we'll go over those at the beginning of class. I will see you next Tuesday.